Okay, as I was telling two people when they were coming in, I did not get the quizzes graded, so I'll give them back to you when we return on Monday. However, I do want to go through the quiz so that you can at least have some idea of perhaps how you may or may not have done. So let's start there today. I'm starting with a blank sheet, so work them as I go. But having said that, I've worked them 2 or 3 times already, so I might get them right. When I make a mistake, please point it out to me. So number 1 says f of x equals print 11x squared minus 13x minus 17 to the 3rd power. Now, one way to do this is that you can expand that. If you expand that, this is a 6th degree polynomial, which means there will be 7 terms. And yes, it can be done, but it's kind of a pain. It's much easier to use the chain rule. F prime of x is something cubed. So the derivative of something cubed is 3 times that something to the 2nd power. And then the chain rule says take the derivative of what's inside. Done. Again, if you choose to expand that, it's a 5th degree polynomial, and it's pain in the backside to do. So it said find the derivative. It didn't say expand it down to so there's no parentheses anywhere. Number 2, we have g of x is equal to cosecant cubed of e to the 2x, e to the 3x, e to the 3x over 2x plus 1. Okay. Well, this one is very similar to that. Again, we have something cubed. So g prime of x will be that 3 times what we had before, something squared now, e to the 3x or 2x plus 1. And now the derivative of that something, which is cosecant, and the derivative of the cosecant is minus the cosecant of what we had, e to the 3x over 2x plus 1, times the cotangent of that value, e to the 3x over 2x plus 1. Now times the derivative of the inside thing, which is a quotient. Derivative of the numerator is 3e to the 3x times the denominator, 2x plus 1. Subtract the numerator, e to the 3x, times derivative denominator, 2, over the square of the denominator. So there we've taken the derivative. Yes, we can multiply this cosecant times that cosecant and get cosecant cubed again. Yes, there's a factor e to the 3x that we could take out. Yes, there's probably a, no, I was going to say, yeah, we have this factor of 3, but there you followed all the rules for finding the derivative. We have a quotient inside a function, inside a function. So we apply the chain rule twice and the quotient rule once to end up with what we have. Number 3, h of x is equal to, and this is just the quotient rule, 3x squared minus 4x, 3x squared minus 4x, plus 5 to the 5th power over x squared minus 3x minus 7 to the 3rd power. Again, we have a quotient, but we also have chain rule in the numerator, chain rule in the denominator. So h prime of x is derivative of the numerator is 5 times 3x squared minus 4x plus 5 to the fourth power, chain rule, 6x minus 4, times the denominator, x squared minus 3x minus 7 cubed, plus, still in the numerator, minus the numerator, 3x squared minus 4x plus 5 to the fifth, times derivative of the denominator, which is 3 times x squared minus 3x minus 720 squared times its derivative, 2x minus 3, and all of that divided by x squared minus 3x minus 7 to the sixth power. And if we expanded all this, about 2 powers of x squared minus 3x minus 7 could divide out, but we're not going to do that. Leave it like this. Okay. Number 4 is 2 products, 2 exponentials, and 2 logarithms all in there. F of x equals e to the 7x plus 2 times natural log 2x plus 1, subtract 4 to the x log base 5 of 6x plus 1. So this derivative, f prime of x, the first product, first chain rule, we get 7e to the 7x plus 2 times natural log 2x plus 1 plus e to the 7x plus 2 times derivative of logarithm, which is 1 over 2x plus 1, chain rule, 2 in the numerator. Now we're going to subtract this next product. Derivative of 4 to the x is 4 to the x, chain rule says we put log 4 there as well. Second factor, log 5, 6x plus 1, plus, but we're subtracting, so it's going to be minus 4 to the x. Derivative of logarithm is 1 over what we had before, 6x plus 1. Because it's not base e, it's base 5. We have to also divide by natural log of 5. And then the chain rule, derivative of 6x plus 1 is 6. So, derivative product gives you 2 factors, or 2 terms. Derivative product gives you 2 terms. Okay. Number 5. We'll put numbers here. Oh, I didn't do that. Number 2. Number 3. Number 4. Number 5. G of x is the inverse sine of the inverse tangent of, not the inverse tangent, but just the tangent of 2x close. The derivative, g prime of x, the outermost function is the inverse sine. Its derivative is 1 over square root 1 plus x, which is tangent of 2x. 1 minus x squared times the derivative of this, Derivative of that is secant squared of 2x, chain rule 2. So we follow the form for the inverse sine. 1 over square root 1 minus x squared. We apply the chain rule to what's inside the argument. Derivative of the tangent is secant squared. And then chain rule, what was inside the tangent. Secant now is 2. Okay. Number 6. H of x is equal to the secant of the inverse tangent of 3 times x, close quotes. So, h prime of x, derivative of the secant is the secant tangent, secant of what we had before, inverse tangent of 3x, cotangent, secant tangent, tangent of inverse tangent of 3x, close. Now, chain rule of what's inside, the derivative of the inverse tangent is 1 over 1 plus 3x squared times, chain rule one more time, derivative of 3x is 3. And find the 6th derivative of f of t. F of t is equal to 3 times the cosine of 2 times x. 2 times t. Okay. One of the things about the sine and the cosine functions is that their derivative is cyclic. We start with the cosine, minus sine, minus cosine, plus sine, plus cosine. We're back to where we started. Through 4 derivatives, we're back where we started. So 2 more derivatives would give us what we need, but there's only one complicating factor, and that is it's not just cosine of t, it's cosine of 2t. So each time we find a derivative, we get another factor of 2 outside. So here we go. F prime of t is minus 6 times the sine of 2 times t. F double prime of t is minus 12 cosine of 2 times t. Triple prime of t is plus 24 times the sine of 2 times t. 4th derivative, fiv of t, is 48 times the cosine of 2t. f5 fb of t is minus 96 sine 2t. And finally, f6 vi t is minus 192 cosine 2t. Okay, so that was the quiz. Like I say, I have not put much of it into grading it, but I will have it back for you next Friday. Next Friday. How about next month? Week Monday. Next time we meet. Often I define tomorrow in a college class as the next time we meet. So if I say tomorrow, in this case it's 12 days hence. next time we meet, you'll get these back. Any comments before I erase all this? Most of you have it written down or scribbled down someplace. Because when I return the quizzes on Monday next, we probably won't take time in class to go through them again. So, okay. All right. Well, we were last working on related rates. So I want to work a couple more related rates problems before we discuss the new material, local linearization. So, on that note, let's just turn to, I want to say it's page 203, maybe a few pages before that, in that neighborhood. Open the book, I'll be more specific. Exercises on 3.10. 196. Well, that was in the vicinity at least. First year I taught school, I had a 7th grade math class in there. And I had one kid, 7th grade, could not read the page numbers in a book. And I'm thinking, you know, they didn't equip me to teach a kid who's 12 years old how to read the numbers in a book. You know, I kind of thought they'd all be able to add, subtract, and multiply and divide by that time, but wasn't the case. So let's look at on page actually 198, number 32. So the strategy here, I think, let's always, when it's talking about applied problems like this, it doesn't hurt to draw a sketch and see what's going on. So we have a dock, and we have a rope coming down to a dinghy, a wash in the deep briny, and from the winch to the top of the boat level is 6 feet. At the current time, this is 10 feet. And this is being hauled out at 2 feet per second. That is, this is also, because this is not a compound pulley. So if it's 2 feet per second here, it's 2 feet per second here. So that's velocity, which is rate of change of x with respect to time. 2 feet per second. Well, let me change this. H for hypotenuse is moving 2 feet per second. If we call this distance x, what I want to find is dx dt. How fast is the dinghy moving toward the dock when the rope here is 10 feet? And the velocity of the rope is being pulled is 2 feet per second. This remains constant. But disregarding the slightly less than flat Earth, we'll consider a flat Earth problem, so that's a right triangle. And in a right triangle, there's a relationship between this length, and x. Namely, x squared plus 6 squared square root is equal to the hypotenuse. So now if I take the derivative of this with respect to time, I get dh dt, and this is a function with respect to time, but it's a square root. Derivative of square root is 2 over the previous square root, or 2 times previous square root in the denominator, times the derivative of what's inside, which is 2x. Well, those 2's divide, so that's okay. And chain rule, dx dt. Well, let's look at it. X is equal to the square root of h squared minus 6 squared. I think that will work better. So, finding this derivative, we get dx dt. What we're looking for is equal to 2 times square root h squared minus 6 squared over 2h. I like that better. And then dh dt. So, this isn't wrong, but I don't know what x is. That's necessary. Well, I can find out what x is because I know when this is 10, that is 6, and x is 8. So I can still get to dx dt. This way, I just have to plug in what h is to find dx dt. So dx dt, that divides, is equal to dh dt is 2 over square root, and it says when the hypotenuse is 10, 100 minus 36 times dh dt. Oh, that's this. What's 100 minus 36?
64.
What's square root of 64?
8.
Wow. X equals h squared minus 6 squared. Take the derivative of both sides, dx dt equals 2h over square. Oh, here's my problem. I have an h here. Times 20. This reduces, divide by 4, 5 halves. Okay. So, this is moving faster, because this is moving 2.5 feet per second this way, as that moves 2 feet per second at this point in time. As it gets closer, this thing actually speeds up. And, do a little arithmetic here. When this is 6 feet long, then it has smashed into the dock at that instant. And if we put 6 in for h, what do we get in the denominator? 36 minus 36 is 0. 12 divided by 0 is infinitely fast. So once again, this is like the ladder that was sliding down the wall the other day. It will not physically slide all the way down the wall if the base sliding out at a constant rate. It has to pull away from the wall, or the top of the ladder will hit the ground at infinitely fast, which would turn you into pure energy. Well, that's how they make superheroes. They just have fall off ladders sliding down walls. Okay. I knew there had to be a way. Okay. So, works the same on, if we use this, we would end up with the same result. Okay. Another one that's a little bit interesting, and I have a story to go along with this one, and it is number where did I see that? It was a balloon being inflated. Oh, that's in the next section, so we won't look at that. So those are kind of the type of problems you want to look at for related rates. Again, what we do is get an equation relating the variables, and when we take derivatives, then we have related rates for variables at particular values. If this were 1,000 feet out, being pulled in, then dx dt would be very close to 2. Slightly greater than 2, very close to 2. But the closer you get to the dock, the faster that's going to be pulled in. So if you have a good crew working for you, they know to quit pulling the rope quite so fast as you approach, so it doesn't dump you into the drink when it smashes into the dock. And of course what would happen is it's going to start lifting you out of the water when it gets real close. Okay, so let's look at a curve. Any old curve, and a point on the curve, and let's call that point x1, y1, and we have a derivative. This is f, this is f prime, or more particularly, this line is y is equal to f prime at x1 times x minus x1 plus y1. That is the equation of this tangent line. Okay. And I know, as I told you, f at x1 is equal to y1. So what is f at x1 plus a little bit? Well, I don't know what f is, so I can't tell you what that is. But I can approximate it on the curve. Let's say if this far is a little bit of change in x, then clearly that is f of x plus delta x. But we also notice that the point on the tangent line is pretty close to the point on the function. And if you're sitting in the back of the room, it may look like just one blob rather than two distinct points. So if we look at a small interval close to the known point, we can use a linear equation to estimate the value of the function at that point plus or minus a little bit. That's a strategy. Let's do something reasonably easy. Let's say, what's the area of a rectangle? Times width. And if I draw that out, I have some length, I have some width. This represents the area inside. If I change the width a little bit, as make it a little wider, or maybe a little narrower, I've grown some. If I change the length a little bit, I've grown some. If I change them both, I've grown some. So, if I call this little space delta L, call this little space delta W, then this space is delta L times W, this space is L times delta W, and this space is delta L delta W. that is the exact area, would be L plus change in L times W plus change in W, delta W. And if you multiply this out as a binomial, sure enough, you get your original LW, and you get plus L times delta W, and you get delta L times W, and you get delta L delta W. That's all the pieces. Well, let's throw some numbers in here. Let's say the length is 80, the width is 40. Okay, so at that, the area at 80, 40, you gotta be kidding me. Excuse me. Yes. I have an appointment Friday morning. Okay. Now get to go see my heart doctor. Now, having said that, there's nothing wrong with my heart, but once you're on their list for whatever reason, you get to go back forever. And the good thing is, when your doctor makes you another appointment, you know you're going to live till the next time. So he made me an appointment a year ago for the 22nd. But he called me up, or his nurses, office people called me up a couple of weeks ago and said, well, we've moved it to the 15th. Makes you wonder, don't think I'm going to make it to the 22nd. So I have to go on Friday and find out if I'm going to make it to the 22nd or not. If he makes another appointment another year, I'll be okay. Okay, but anyway, we have this, and it is 80 times 40, which is 3,200 square units. If it's feet, it's square feet. If it's centimeters, it's square centimeters, and so on. But at 80 plus a little bit, and let's go on and decide what a little bit is. Let's say a little bit here is 1, a little bit here is 1/2. So 80 plus 1 times 40 plus 1/2. In other words, it's no longer 80 by 40, but it's 81 times 40.5. Well, multiply all this out. Sure enough, we get 3,200, and then we get plus 40, and then we get another plus 40, and then we get a plus 1/2, which adds up to 3,280.5. Was that half really worth very much? Nah, let's just throw it out. Let's throw out that higher degree term. Because if we're really making small changes, that's not very much. Let's say instead of a foot and half a foot, it was 1/10 of a foot and a 20th of a foot. Then this term would be 1/200 of a foot. 1/200th of a square foot. 32 and some change, and 1/200. Probably toss that out. Okay. When is close enough? That's kind of what we're doing here. Again, when I worked for the Federal Aviation Administration, in order to identify your location within a centimeter anywhere on Earth using global positioning system takes 15 significant digits to pin yourself down to a centimeter. Okay? Which means you need a pretty good number crunching machine to do that. But realistically, does the world come to an end if I move a little over here? That's not a significant change. So how many digits can I toss out? A few. It probably doesn't make any difference. On the other hand, if I'm close to the edge of the Grand Canyon, that does make a difference. So there are some applications where we don't care about the nickel and dime stuff. And other applications where we do care about the nickel and dime stuff. So when we do care, then we want to crunch through all this arithmetic or algebra to get our best answer. When close is good enough, we don't care about higher order terms. We care about the first order changes, but not the second order changes, or third order, or fourth order, depending on how many variables there are in the equation. So, let me introduce a new concept. And it's another application of the chain rule. So I have y is equal to some function in x. Then let's take derivative with respect to t. I have dy dt equals f prime of x dx dt. That's chain rule. The derivative of x with the derivative of f with respect to t times dx dt. That is rewriting it, dy dt equals df dt. I'm sorry, df dx df dx dx dt. Effectively, that divides out. So, but before I divide that out, if I multiply through by dt, I have dy equals f prime of x dx. And this is a differential equation, and these are called differentials. Of course, if we let, from the definition of derivative, if we let the change in x approach 0, then we have 0 is equal to something times 0. It's not very interesting. But in application, we use this to get to that point quickly. Let's look at this function again. Area is equal to length times width. If I take the derivative of all of these with respect to a dummy variable, dA dt equals product L, well, that's a dl dt times W, using product rule, dl dt times W plus L dW dt. Again, multiply through by dt. dA equals dl W plus L dW. That means the change in area is approximately equal to B, well, no, not B, change in L times W plus L times the change in W. Now this is approximation. It was a linear approximation. this process of using a linear approximation is called local linearization. It goes along with the first picture we have up here. We find the derivative of the function, or we make a prediction about what the function will be by only making little changes. Then we move. A full motion simulator, aircraft simulator, and I have flown 747s, 737s, 727s, DC-10s, and Airbus 320 and Airbus 340. I've flown all those. I've crashed all of those. I've also landed safely in all of those. Nice thing is when you're in full motion simulator and you do something stupid, crash, you just hit the reset button and go again. But how do those work to give you such a lifelike experience of flying? You can actually get your pilot's license never having flown an airplane if you have a level 6 full motion simulator that you learn on. They got to be pretty good to allow you to do that. Well, let's think about that. You have thrust, you have drag, you have lift, you have gravity, you have pitch, that's nose up, nose down, roll, left, right, roll, left, right, yaw, nose is going this way, that way. Okay. 1, 2, 3, 4, 5, 6, 7 things to worry about. If, and this is usually considered constant, so maybe it does. But if lift changes, if lift exceeds gravity, you go up. If lift is less than gravity, you go down. If you pitch up, for a while you increase lift, so you initially rise, but you start losing airspeed because you're fighting gravity, so then you'll have a tendency to roll over. So an airplane in level flight actually is doing more like a sinusoidal path. It climbs a little, drops a little, climbs a little, drops a little, but this is just a few feet. No big deal when you're 35,000 feet up. Unnoticed by the passenger is how little it is. Okay. But if you suddenly have to pull a 2G turn, passengers kind of notice that. I wish they would do that some when I'm flying on an airline. Because I mean, you pay good money to fly on an airline, don't you? Shouldn't you have a little fun while doing so? I mean, you don't want to be so scared that you wet your pants. But, you know, I paid $600 for this flight. I want to have a little fun. You know, give me a couple of G's, not 7 G's. I'd black out at 7 G's. You know, at one time, I sure I wouldn't, but these days, you know, more than a couple of G's, and all of us probably be hurting. Okay, so, and the way they adjust all of these is exactly like this. They put in a value for lift and thrust and drag and gravity and pitch and roll and yaw. And then they say, if we change this a little bit, change this a little bit, change that 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 a little bit. What do all these changes do? What moves you on each curve from there to there plus a little bit, which if that little bit of change is close enough, you can hardly tell the difference between what the actual position would be and what the estimated position would be through local linearization. Okay? And that's how simulators work. Those 6 axis of motion that they talk about on simulators is based upon linearization of functions. If the acceleration changes a little bit, what does it do to the velocity? If the lift reduces a little bit, what does it do to the velocity? If the roll increases a little, what does it do to the rate of turn? all those things, every one of them's done with that, internally. Which is the same as this, internally. Which is the same as this, internally. If we go one more, so now let's work that problem again. Let's say that, again, we started with, area was 80 by 40, was 3,200, length times width. And let's say we make a little bit of change, area at 80 plus 0.1 and 40 minus 0.1. Well, that says that the new area is approximately the old area plus 0.1 times my original W, 0.1 times my original W, 40, plus minus my original 80 times 0.1. So it suggests that's 4, this is minus 8, 3196. And the one that I missed, 0.1 times minus 0.1 is minus 0.01. So more precise, but isn't 3196 okay as compared to 3195.99? If you're pulled over for speeding, going 3,196 centimeters per second, what you had in your car, no, I was actually going only 3195.99 centimeters per second. Do you think the judge would worry about that 0.01? No, you'd still get the ticket. What? How fast is that? Move it over 2 places, 31 meters per second, which is over 90 miles an hour. I'm sorry, over 60 miles an hour. Because 88 feet per second is 60 miles an hour. So that's, you know, maybe 65 miles an hour. In a 25 mile an hour school zone, not a good move. If you're driving that slowly out on the interstate, you'll get run over from behind. Okay, so let's do one more of these. Like I say, let's go to 3 dimensions. But the strategy is precisely the same. Let's go to a rectangular solid. And let's make it pretty simple. Let's say this rectangular solid is 8 by 6 by 4. So the volume of this rectangular solid, length times width times height, is 8 times 6 times 4 with your appropriate cubic units. 48 times 4 is 192. Saw that number earlier tonight. But what do we have if I look at dV? The differential of V. Triple product. dL WH plus L dWH plus LW dH. That represents, if I change the length a little bit, I kind of put an additional slab on the back. If I change the width a little bit, I put an additional slab either here on the front or backside there. If I change the height a little bit, I either tack on something on the top or on the bottom. So those are those 3 pieces. But if I put something on here and something on here, you see that I've left off the piece here. Okay. And if I change all three things, I end up with a box that is change in L, change in W, change in H. So I end up with, let's multiply this out. L plus change in L times W plus change in W times H plus a change in H, A plus a change in A, equal all that. Well, let's see. These two give me LW plus delta LW plus L delta W plus delta L delta W times H plus delta H, which gives me LWH, what we already had, plus delta LWH plus L delta W H. Now this times this is plus LW delta H, and now some other terms. This times that. Well, let's go. This times that, I get plus delta L W delta H plus L delta W delta H plus, I'm missing one here. Should have three first order, 1, 2, 3, 3 second order, delta L delta W times H, and 1 third order, delta L delta W delta H. So the more variables in the original function, the more higher order terms of change you have to account for all the change. This change equation has 1, 2, 3 first order changes. It has 1, 2, 3 second order changes and 1 third order change. Well, if we're using linear approximation or local linearization, we don't care about orders of change higher than the first order. We just throw them out. Because if we're kind of on the same magnitude as we did the last problem, that these deltas are in the order of a tenth, then these changes are in order of a tenth, a tenth, a tenth. But this is order of a hundredth, a hundredth, a hundredth. And this is on the order of a thousandth. So if we're willing to throw away or keep the tenths, but throw away the hundredths and thousandths, we're good to go. So let's do this problem. Like I say, we have the problem, we have its dimensions. Let's change its dimensions by a little bit. So let's change our length by 0.1. Let's change our width by minus 0.1. And let's change our height by plus 0.2. Now to get the exact value, we have to multiply all those out. We have to get these 8 terms. 1 we know, 7 we don't know. But We can do it 8 terms when we multiply all that out. But we don't want to do that. We want to say, well, this is about the same as the original length times width times height plus width times height times the change in length plus length times height times the change in width plus length and the width times the change in height. And we know these values. 192 plus 24 times 0.1, 2.4, plus 8 times 4 is 32, actually minus 3.2, plus length times width, 48 times 0.2, 96, 9.6. So we would estimate this value at, well, what's 3.2 from here is negative 0.8. Negative 0.8 from here is 8.8. So 200.8. Did I multiply those right? Did I add right? Minus 0.8. 0.8 subtract from 9.6 is 8.8. And 8.8 added to 192 is 200.8. So that's my estimation. Let's compare it to the actual value. The actual value, let's see. I want 8.1 times 5.9 times 4.2. Let the calculator do the hard work, and it says 200.718. Is that close enough? We'll actually miss that by almost a tenth. But 4 digits over. That close enough? Yeah. If I were trying to decide how much paint I need to paint this whole thing, I'd probably round that up to 210, so I'm sure to have enough paint to cover all of it. Oh, to fill it. This is not surface area, this is volume. Local linearization. Let's do one. In that section, that's where I think 203 came in. Yep, it's talking about there. The problems are on page, on over a little bit, and let's see. What number did I see? Well, there's one here that is talking about the rate of change of the radius. Oh, it was a rate problem. So let's go back in the previous section. There's one in there that I know it's in here. Some years ago, some of my peers in my office on other people's offices' birthday, on their birthdays, they would fill their cubicle with balloons. You know, your near-death type balloons, your over-the-hill type balloons, fill their cubicle full of them. Well, my boss his birthday was coming up, and he was going to be out of town on his birthday. And he says, under no circumstances can you put balloons in my office. Well, the boss has spoken. You can't put balloons in his office. So while he was gone, someone came up with the idea, someone I know very well, why don't we just put one balloon in his office? So we put one weather balloon in his office. He gets back from his trip, opens his office door. He says, you know, the famous word. I said, you guys got me. I said no balloons, and this is not balloons. It's just one balloon. But then he made a mistake. Rather than undoing the nozzle and letting it bleed out slowly, he took out his pocket knife and stabbed it. Weather balloons, anybody know what they have inside lining a weather balloon? They put a little talc powder in there to keep the latex from sticking to itself before it's inflated. So when he went poof, the balloon went poof, and the talcum powder went poof. Needless to say, that was the end of the balloon episodes forevermore. And he said, I have no one to blame but myself, so he took it well. But I was not a fan of the ongoing balloon crisis. But, you know, if you can't avoid them, then join them, you know? So I'm afraid I misbehaved. Anyway, so where is that one? Let's see. I worked one like it earlier. Anyone see the balloon problem on related rates, commercial air traffic?
Radius of an inflating balloon?
Yeah, what number is it?
31.
31, okay. Well, the picture, how could I not see that picture? Okay, a balloon and a bicycle. No, 31, the radius of an inflating balloon. A spherical balloon is inflated with helium at the rate of 100 pi cubic feet per minute. How fast is the balloon's radius increasing at the instant the radius is 5 feet? And how fast is the surface area increasing? Okay, so they tell us the rate of change in volume. dV dt is 100 pi cubic feet per minute, did it say? And they want to know what is the rate of change of the radius with respect to time, and they want to know what is the rate of change of the surface area with respect to time. Well, what we need is a couple of formulas. First, the area of the volume of a sphere is 4/3 pi r cubed. And the surface area of a sphere is 4 pi r squared. Interesting enough. Okay. Archimedes told me these when he was quite old and I was quite young. So now we can take the derivative of the first with respect to time. And we get, well, let's see, 3 times 4 pi r squared dr dt. I know dV dt, so I can solve for dr dt. That is 100 pi cubic feet per minute is equal to 4 times pi times r, 5 dr dt. What is 100 pi divided by 100 pi? Oh no, 100 pi divided, 5 squared. 100 pi divided by 100 pi is 1 dr dt. That is 1 foot per minute. 1 foot per minute. Now we want to know how the surface area is changing. And we have a surface area formula. we find ds dt is equal to 8 pi r dr dt. We know ds, oh no, we know dr dt is 1. We know r is 5. 5 times 8 is 40 pi. 40 pi feet squared per minute. You know, every day at local noon they release a weather balloon. They used to do it out at Will Rogers. I think they do it down at Max Westheimer now. But one time, one cold winter day many years ago, when some winter days are sometimes your calmest, you know, and those radio songs, you know, they have a radio equipment on it. And if you retrieve one, you just take it to any post office and it'll get sent back to the proper people. Having said that, on this particular day, the balloon goes up, and 6 hours later, it comes down within 100 feet of its departure point. And you believe Oklahoma had a day that the wind was so light that it just went straight up and straight down. Well, 100 feet. And that could have all been Coriolis at that point, I don't know. Okay, so we have related rates, we have local linearization, and you need the ever infamous practice, 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 practice.